Okay, so hello everybody. Let me put this to full screen and get the laser pointer. Okay, so hello everybody. Yeah, just hope all of you is healthy and fine in given the circumstances. So I'm gonna keep the lesson we started the other day, but you will see that I change actually the second part of the lesson where we will transform our equations to a rotational frame of work. So I will actually I will upload this new presentation into Moodle. Okay, I changed it because yeah, I was looking at it and I think it was not clear enough. So I simplify a bit the things. Okay, I think this way is easier for you to understand without face class. Okay, without actually being on the classroom. Okay, so just to recall what we did the other day. Remember the other day we introduced, we derive the equations of motion. We've seen that the atmosphere can be described with 5 variables, the 3 components of velocity, pressure, and temperature. So we need, and so that we need actually 5 equations to tie these variables, and we derived momentum conservation equations that gave us 3 equations, one for each spatial direction, conservation of mass, and the conservation of energy. So we have 5 equations and 5 variables. This together with the boundary conditions is enough to determine the evolution of the fluid. But we derive everything, we derive all of these equations from an inertial frame of reference. So now what we are gonna do is we are gonna see how to write these equations, but from a rotational point of view, okay? Actually from our point of view, because we, the observers, we are actually over the Earth, so what we are actually observing the atmosphere from the Earth's surface, we are actually observing things moving from a rotating frame of reference. So basically, what as an example, what we'll do is just transform this momentum equation that we have written in here. This is the momentum equation written from the inertial perspective, from an inertial frame of reference. And what we'll do is transform this equation to a rotational frame of reference. So basically, okay, what we have to do is we have to find a relationship between the total derivative of some vector, we have to express the total derivative of some vector from in an inertial frame of reference and in a rotational frame of reference and see how they are related, okay? So this is what we are gonna do right now. Okay, so let's imagine, okay, we have a vector, we'll call it A, okay? And we'll have that this vector in an inertial frame of reference, we can expand it on its components that we'll call A sub x, A sub y, X sub z, and these are the unit vectors E, J, and K. And we will actually express then the same vector, but from a rotating frame of reference just by adding these primes here, okay? But now look, now that is important that in the left-hand side, so this is the same vector, okay? We are just trying to describe the same vector, just from a different point of view, okay? From a different frame of reference. So the vector is the same. A is A, okay? We are just putting these primes in here to distinguish the components, and then we will relate, okay? So let's just start from our inertial frame of reference and let's calculate the total derivative of this vector respect to the t. in a total general way, okay? So in a general way, here this term, okay, is the sum of three terms that consists of a product of two quantities, okay? Of two, not quantities, let's call it two things maybe, okay? I don't know. The component, so basically the I sub x, the magnitude of the component in the e direction and so on. So we have to apply the derivation product rule. So basically we derive that and we get that this is the first component multiplied by the derivative of the second plus the second without derivative, with second multiplied by the derivation of the first, and the same for the rest of the components, okay? So the total derivative of a vector generally should be expressed in this way. But like we are in a frame of reference, by definition, a frame of reference is a frame in which the derivation of these three unit vectors equals 0, okay? It is fixed on space, okay? So then if we just go back to this expression in here, we see that the first terms, okay, the derivative of the unit vectors are equal 0. So our total derivative reduced to the classical form we all have in mind, this one in here. Now let's do the same, but now from the rotating frame of reference, okay? Remember that our vector, we express it with these primes, which did it this way just to distinguish it, okay? It's easy just for the derivation, just to distinguish it from the vector in the inertial frame of reference. So now again, we apply the derivation product rule, and we found the same expression than before. But the difference now is that now these parts in here, these vectors are not 0 because they are rotating. So these unit vectors E, G, and K, they are actually rotating. So now they change. They change with time. Okay, so these cannot be considered 0 anymore. Now, recall that I told you that these two vectors here are the same. Okay, by definition. So now we can just equal the right hands, these two parts. Okay, so this and this are the same. So we can just equal this to this part on here. I've done this in here, okay. We can regroup terms now. And what we found is that the inertial derivative, okay, so this part in here equals to these terms in here that we will call the derivation of the vector A in the rotating frame plus these components that describe the effect of rotation. Now you see that we already have a relationship between our derivation in an inertial frame of reference in a rotational frame of reference. Okay, so what is left is to find actually what is that. Okay, how we can express the derivative of the unit vectors. So to do that, okay, imagine. So think of each of these unit vectors as a position vector, okay? And just recall from basic physics that the linear velocity equals to the vectorial product of the angular velocity by the position vector, okay? So V equals omega cross product of the position vector. And now, because we know that V by definition is the total derivative of the position vector, okay, we can just equal this with that, and we found that the change of position of the position vector equals to this expression in here, the cross product of the angular velocity and the position vector. If we write this now in components, of course, it is very simple to see that we get this expression here. So we just found that actually this total derivative of the position vectors of these unit vectors can be expressed as this sum of cross products between the angular velocity and the unit vectors. And if we aggregate these terms, this is actually just rho multiplied by this vector. So we found you can look at that, okay? Look at this careful. It is quite simple, okay? It's not difficult to understand. It looks a bit daunting when you look at it. It's like a lot of subscripts and a lot of derivations, but it's not difficult. So just look at that, and you found this relationship, okay? This is a total general relationship that allows to transform the derivative of any vector A from an inertial to a rotating frame of reference. And the only thing to change from one to the other is that it appears this extra term in here. Now, what we can do to express our equations of motion in a rotating frame is substituting this vector A by the vector we are interested in. It's quite simple to see that if you substitute A by the position vector, you get a relationship by velocity. So you substitute here R, dr over dt in the inertial frame of reference is by definition the velocity in the inertial frame. The same here, but in that case is the vector velocity in the rotation frame, and here you have rho multiplied by the position vector R, okay? And now we can do the same, but now what we will do is substitute, instead of substituting A by R, we substitute A by the inertial velocity, okay? So we substitute A by U, by the inertial vector velocity, and we get this expression of here, okay? You can just work this out yourself. It's quite simple. And you basically, what you found is that the acceleration in an inertial frame of reference equals to the acceleration in a rotating frame of reference plus these two extra terms that, if you want, are the effects of rotation, okay? So now we can just recover our equation of motion. So the equation we've seen here before, and we substitute du dt by this expression in here, okay? And we get now this equation where that is basically the momentum equation, but from a rotational frame of reference point of view. And now these two terms, okay, these two terms that appear, they are just due to the effect of rotation, but it's quite useful to think about them as forces, okay? These terms are what is called an apparent force, okay? It's not a real force. It appears because we are in a rotating frame of in a rotating frame of reference, but it is useful to think about them as real forces, okay? And these two forces, this one in here is what it's called the Coriolis force. I think probably most of you have heard about. And this one in here is the centrifugal force, okay? Or centrifugal acceleration, if you want. Let's try to understand these forces. So let's start just by the centrifugal acceleration, okay? What we will do with the centrifugal, what it's done, okay, with this centrifugal acceleration is just add it to the gravitation force. And then together, when you add one to another, you get a new force that you will call actually the modified gravity, okay? So look at this here on the left side, look at this scheme here, look at this drawing here. So this is basically the planet, okay? Here we have some particle of air, okay? This is our position vector, okay? That is the distance to the rate of rotation in here, okay? From the rotation axis, sorry. okay? And you see that here we have the gravity always pointing to the center of the planet, okay? But if you sum these two forces, the gravitation plus the centrifugal force, you get this modified G star, okay, force. Okay, that you see that is proportional actually to this term here. Okay, it's proportional to the square of the angular velocity multiplied by the distance of this particle to the axis of rotation of the planet. Okay. And now what we can do is we can build, like we did before, a modified geopotential. Okay. Remember that, well, generally every vectorial space, okay, can be transferred to a scalar space, okay, and any derivative, spatial derivative over this scalar space will return us to the vectorial space. Okay, so what we do is, as we did in the case of gravity, where we define the geopotential field, we will now define a modified geopotential field. Okay, and this is just what we did before. The force, okay, so G acting on the Z, the unit vector direction Z, equals to the gradient of GZ, where now Z is not a unitarian vector, but is actually a distance, a coordinate, okay? So the gradient of GZ on where GZ is the potential field, the gradient, it gives us this vectorial field, okay? So you see that the gradient, spatial derivative of a scalar field give us a vectorial field. This is totally general, it's a general property in mathematics, okay? But in that case, we apply it to gravity. And the same we can do for the centrifugal acceleration, okay? So here we have the centrifugal acceleration that can be expressed as the gradient of this centrifugal potential field, if you want to call it, okay? So now if we adapt these two, we get actually, what we get is just this expression in here, okay, where you see that actually R equals A. So here we have R equals, it's close to A cosinus of latitude, where A is the distance, is the radius of the planet Earth, okay, and we suppose that the distance, so the altitude, the height of the particle compared to the radius of the planet is quite small. Okay? You can just work this out here. And we just get this modified gravitational potential. If we divide now by G, by the gravity constant, we get this modified geopotential height. And this here, this is just a plot, okay? This is a map of actually the modified gravity, okay? You see, this is the blue are actually smaller values of gravity, and the red are higher values of gravity. And you can see that there is a meridional, a clear meridional gradient on the strength of of gravity, okay? And this is due of the modified gravity. This is basically due to this term in here. You see that this term involves a cosine, and of course a cosine of 0. So cosine in the equator when latitude is 0 equals 1. So then this is bigger. So then this is subtracted to GZ. But when we are close to the poles, cosine of 1, cosine of 90 equals 1. Cosine of 90 equals 0. So then this term is 0. So then actually the geopotential field equals GZ. So it's larger. And this is what this plot shows. There's also a small differences due to the distribution of mass. You see that here, for example, you can clearly see the Andes chain. Here you can see, for example, the Tibetan plateau. Okay, but now you see here, for example, you can see Greenland, Antarctica. But still, anyway, the main dependence is on latitude. And The second apparent force, and very important one, we will come back to this term quite often, is the Coriolis acceleration. Okay, remember that this term is expressed as the cross product of the angular velocity multiplied by the by u, the velocity vector. Okay, and then this this factor appears in here. So the first thing we can see, okay, is that by definition of vectorial product, we see that actually the Coriolis force acts in a perpendicular direction to the velocity, okay, in the same plane and in the perpendicular velocity, in the perpendicular direction of velocity, and its strength is proportional to velocity. Because remember that the magnitude of this vectorial, this cross product, is actually 2 gamma u multiplied by the sinus, by the sine sinus function of the angle between these two vectors. Okay. So if you would have a particle in here, okay, imagine we have a particle of air that is moving north from the equator. Okay, as it accelerates, as it increases its velocity, the strength of the Coriolis force will increase, and the particle will tend to deflect, to be deflected to the right in the northern hemisphere, while in the southern hemisphere, it will actually tend to bend the particle to the left. Okay. Now we can develop, we can expand, actually, we can expand this Coriolis force and see that we can do some simplifications. If we express now the Coriolis force in a spherical frame of, in a spherical coordinates, okay, so these are our spherical coordinates. This is our local Cartesian system, z, x, y, in the meridional direction. This is, of course, related. This is the transformation between this Cartesian coordinate system to our spherical system. Okay, you can just work this out. I'm sure all of you have seen that before. And basically recall that this lambda is longitude, this phi is actually the latitude, and a is just the distance of our Cartesian frame of reference to the center of the planet. In that case is where we center our spherical frame of reference. Okay, so by developing this term in here, okay, the cross vectorial product of the Coriolis force, we just can develop it. Okay, we found actually, so this is just a projection of rho into this frame of reference in here, okay, plus the UVW, the velocity field, this term in here. We found this expression where you see that actually this is the x term. So this is the Coriolis force on our longitudinal direction, the Coriolis force in our meridional direction, and the Coriolis force in the vertical direction. What simplifications can we do? Well, we can just right away eliminate the vertical component. This is actually due to the fact that the magnitude of the Coriolis force that acts on the vertical direction is much, much smaller. It's orders of magnitude smaller of g. That is the other force acting on the vertical direction. So it's negligible. And also we can eliminate any term that contains w. So that contains vertical velocity, because the vertical velocity is about 2 orders of magnitude smaller to the horizontal components of the velocity. Okay? So these two terms can be eliminated, and this gives us this simplified version of the Coriolis force, that is that the Coriolis force can be expressed as these two terms in here. It's only acting on the horizontal plane and can be expressed as 2 rho sinus of the latitude multiplied by the meridional component, and then in the meridional component is 2 rho sinus of latitude multiplied by the zonal component of the velocity. This is just the vectorial form of this vector in here. And now we see that we can factor out actually this term that is repeated, two gamma sinus of latitude, gamma, 2 omega. I was calling gamma all the time. Sorry, it's 2 omega. And this, it's a parameter, okay, that it's called a Coriolis parameter, okay? And it gives us an idea of the magnitude of the Coriolis force, the magnitude of the Coriolis force in any place on Earth where we are interested in it, okay? So we can already see some interesting things in here, okay? So we see that the magnitude of the Coriolis force is proportional to F, and actually is proportional to velocity and F, so it scales, okay, with the latitude. So when we are very close to the equator, latitude is equal to 0, so sine of 0 is 0. So then basically we don't, there is the magnitude of the Coriolis force in the equator is 0. At it increase, okay, it increase as it increase in a homogeneous way. In the same rate, let's say it increases as we move towards the poles. Okay, this is actually, you will see that this actually it's very important. Okay, because the Coriolis force has it imposes an important constraint in the fluid, in the movement of the fluid particles. So different movements will occur generally in mid latitudes or high latitudes in general when we have a very strong Coriolis parameter than in the equatorial regions where we can neglect, pretty much we can neglect the effect of the Coriolis parameter for some movements in some occasions. Okay, so let's just review the full set of equations, in that case expressed from a rotational point of view. Okay, we have here the horizontal momentum equation, and this is important. Look now that I put here as this subscript H, okay, that basically means that is the horizontal. So these are this is the vectorial expression, okay, of the velocity of the momentum equation in the zonal and meridional plane in X or Y direction. Why is that? Because actually in the vertical direction, most of the time we will just assume that we have hydrostatic balance. Okay, so our equations are going to be the hydrostatic balance in the vertical plus this equation, this horizontal momentum equation that becomes 2 in its component form, that we will express in this sub-H index. This is in height coordinates. Okay, so we are basically expressing the pressure gradient force as over surfaces of constant Z. But remember that we can substitute the vertical coordinate from Z to P, and by doing so, basically what we do, recall that we just get a different expression from this force in here, okay, where now it is expressed as the gradient of the geopotential height in a pressure, in a constant surface pressure. We will go from one to the other indistinctively, okay, but remember that intuitively it is easy to go from one to the other, okay, when we think in the terms of the horizontal forces that are applying over a constant Z or over a constant P surface. And then we have the continuity equation and the thermodynamic equation that they do not change by going from an inertial to a rotational frame of view. So the forms that are basically, so that the structure, I mean, expression of these two equations remain the same. Okay, so that is all for today. We already have seen, okay, all the equations of motion. So just to recall a bit, Remember that we've seen these 5 variables, as I said at the beginning, that have 5 equations. We derive these 5 equations first from an inertial frame of reference, and then we add the effects of rotation, which just add these 2 terms, the Coriolis acceleration and the centrifugal acceleration, to our momentum equations. And we then seen that these 2 terms that come, these 2 terms that express the effect of rotation, we can think of them as an apparent force, the Coriolis acceleration and the centrifugal acceleration. And at the end, we get the complete set of equations. So that is all for today. Next lesson, I'm gonna upload it to the Moodle. I'm gonna upload actually a lesson on balanced flow. Okay, so we will use these equations together with some simplifications to try to understand some typical movements of the atmospheric flow in the atmosphere. Okay, thank you very much. And as always, just please don't be shy and write comments on Moodle or send me an email. If you want to do it in private, send me an email. If not, you can just put a Moodle message so everybody can have a discussion. Okay, thank you, bye.